Every time you board a flight, pull up directions on your phone, or look at images from a rover on Mars, you are relying on an invisible infrastructure of code. It governs the logistics of our entire physical world. Yet beneath the interfaces and algorithms, the physical hardware of a computer is remarkably simple. At the processor level, it only understands the presence or absence of electrical current, binary ones and zeros. In the early days, speaking to a computer meant speaking its language directly. Using first-generation languages, programmers drafted machine-specific instructions by physically punching holes into paper cards or manually plugging cables into switchboards. This was a grueling process. John Backus, an early computing pioneer, described it as hand-to-hand combat with the machine. A single error in binary math or one hole punched in the wrong column would cause the entire program to fail. To realize our more ambitious goals, we needed a bridge between human logic and machine execution. We call that bridge abstraction. By the 1950s, the computing industry faced an economic bottleneck. These room-sized machines were expensive, but the sheer human labor required to write, test, and fix their code often cost even more. Backus, working at IBM, proposed a practical solution: a programming language that captured the mathematical intent of the programmer rather than the mechanical needs of the computer. Fortran introduced an optimizing compiler, software that takes a standard algebraic equation and automatically translates it into binary code. The gains were massive. A process requiring 1,000 hand-coded machine instructions could now execute with just 47 lines. Fortran proved that software could be detached from the hardware. It turned programming from mechanical engineering into applied mathematics. A new bottleneck quickly emerged. As companies manufactured different models of computers, software remained locked to the specific brand it was written for. Upgrading your hardware meant rewriting your entire software library from scratch. In the early 1970s, Dennis Ritchie and his team at Bell Labs developed a solution called the C programming language. Here, C struck a precise technical compromise. It offered the high-level abstraction needed to write complex logic quickly, but it maintained the execution speed of raw assembly code. C introduced the concept of portability. Because of its design, an entire operating system like UNIX could be written once, and then routed and deployed across entirely different machines. By pulling the operating system up and away from the bare metal, C broke the hardware monopolies. Software architectures could finally outlive the physical machines they ran on. As the internet connected the globe in the 1980s and 90s, software projects grew to involve hundreds of dispersed developers. Relying on long procedural lists of instructions resulted in fragile code bases, often called spaghetti code, that would collapse under their own weight. To prevent these system failures, the industry climbed another rung up the ladder, adopting object-oriented programming. Object-oriented programming relies on encapsulation. Instead of writing an endless list of commands, developers bundled data and functions into secure, self-contained objects. Because these objects operate independently, dispersed teams can build, modify, and reuse code simultaneously without breaking their colleagues' work. Object-oriented programming solved a scaling problem. It abstracted the organizational complexity of human teams, allowing for the construction of planetary-scale applications. All of these languages are what computer scientists call Turing complete, meaning they can all theoretically solve the exact same logical problems. So why haven't we just picked one and consolidated? Developers need to reach for different rungs on the abstraction ladder based on the problem. When you write software for a network router or an engine sensor, where raw speed and strict memory control are required, you reach down the ladder to C. Conversely, when a multinational bank needs to deploy a global web application, they reach up the ladder to highly abstracted languages like Java or C#, prioritizing collaboration and organization over processor speed. Even the oldest languages survive for specific reasons. Right now, COBOL is still processing transactions for thousands of global financial systems. Banks leave these legacy programs in place because decades of continuous use have proven they will not crash. The climb continues with fifth-generation languages, where we abstract logic itself. Instead of writing an algorithm, programmers define a set of constraints, the conditions that must be met, and leave it to the computer to find the logical path that fits them. The multitude of programming languages we use today forms a specialized ecosystem. a map of our relentless effort to make machines bend to human imagination.